According to the National Electrical Code, the statement regarding ground rods at a separate building supplied by a 60-amp 4-wire feeder is technically false. The NEC Section 250.32b2 specifies requirements for grounding electrodes at separate buildings or structures. This section generally mandates the installation of grounding electrodes at each building or structure supplied by a feeder or branch circuit. This is to ensure a low impedance path to ground for fault currents and lightning surges. When a building or structure is supplied by a feeder or branch circuit, it's essential to establish a local grounding electrode system. This system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are connected to the building's grounding system. The purpose of this local grounding electrode system is twofold. Firstly, it provides a path for fault currents to return to the source in the event of a ground fault, and secondly, it helps to dissipate lightning energy safely into the earth, protecting the building and its occupants from electrical hazards. Bonding the grounding rods to the grounding bar in the panel at each outbuilding can provide a path for lightning. However, it doesn't eliminate the need for ground rods. Ground rods are specifically designed to provide a low impedance path to ground and to dissipate lightning energy safely into the earth. It's important to understand the difference between grounding and bonding. Grounding refers to connecting electrical equipment or systems to the earth through a grounding electrode system, while bonding refers to connecting different metallic parts of the electrical system together to create an electrically conductive path. Grounding electrodes, such as ground rods, are installed to provide a direct connection to the earth, allowing fault currents and lightning energy to dissipate safely. Bonding, on the other hand, ensures that all metallic parts of the electrical system are at the same electrical potential, reducing the risk of electric shock. Installing ground rods at each building and bonding them to the grounding bar in the panel is a good practice to protect equipment from lightning damage. However, ground rods are not intended to clear ground faults. Ground faults are cleared by the overcurrent protection devices in the electrical system, such as circuit breakers or fuses. Overcurrent protection devices are designed to automatically interrupt the flow of electricity in the event of an overcurrent condition such as a short circuit or ground fault. These devices protect the electrical system and prevent damage to equipment and property. In the event of a ground fault, the fault current flows through the grounding system back to the source, tripping the circuit breaker or blowing the fuse. This interruption of the current quickly stops the flow of electricity and prevents further damage. Therefore, while grounding rods play an important role in providing a path for fault currents and dissipating lightning energy, they are not responsible for clearing ground faults. Ground faults are cleared by the overcurrent protection devices in the electrical system. According to the NEC, there are specific requirements for the size and type of grounding electrodes. For example, ground rods must be at least 8 feet long and made of specific materials such as copper or galvanized steel. The NEC also specifies the minimum number of grounding electrodes required, as well as the methods for connecting them to the grounding system. In addition to the requirements for grounding electrodes, the NEC also includes requirements for bonding. Bonding is the process of connecting different metallic parts of the electrical system together to create an electrically conductive path. This path allows fault currents to flow back to the source, tripping the circuit breaker or blowing the fuse. The NEC specifies the types of bonding conductors that are permitted, as well as the methods for connecting them. For example, bonding conductors must be made of copper or other approved materials, and they must be sized according to the size of the circuit conductors. The NEC also includes requirements for bonding specific types of equipment, such as metal water pipes, metal gas pipes, and metal building frames. Bonding these types of equipment ensures that they are at the same electrical potential as the rest of the electrical system, reducing the risk of electric shock. It is important to consult the NEC for the specific requirements for grounding and bonding in a particular application. The NEC is a complex document, and it is important to understand the requirements before installing any electrical equipment or systems. Furthermore, local codes and regulations may have additional requirements that must be followed. Grounding and bonding are essential components of any electrical system. They protect people and property from electrical hazards, such as electric shock, fire, and equipment damage. By following the requirements of the NEC and other applicable codes and regulations, you can ensure that your electrical system is safe and reliable. In summary, ground rods are required at a separate building supplied by a 60 amp 4-wire feeder, even if the neutral is floated to the separate building disconnect, as per NEC section 250.32b2. This ensures a low impedance path to ground for fault currents and lightning surges. While bonding the grounding rods to the grounding bar in the panel at each outbuilding can provide a path for lightning, it does not eliminate the need for ground rods. Ground rods are specifically designed to provide a low impedance path to ground and to dissipate lightning energy safely into the earth. Ground rods are not intended to clear ground faults. Ground faults are cleared by the overcurrent protection devices in the electrical system, such as circuit breakers or fuses. Always consult the latest edition of the NEC and local codes for specific requirements and ensure that all electrical work is performed by qualified personnel. The function of a ground rod is to provide a path to earth for electrical current, both from fault currents and from lightning strikes. Firstly, for fault currents, in the event of an insulation failure within an electrical device or wiring, a fault current can flow to ground. The ground rod provides a low impedance path for this current to return to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to trip and to energize the circuit. This protects equipment and personnel from electrical shock and fire hazards. Secondly, for lightning strikes, lightning is a powerful and unpredictable force of nature. When lightning strikes a building or nearby, it can induce high voltages in the electrical system. Ground rods provide a path for this energy to dissipate into the earth, protecting the building and its contents from damage. Without a proper grounding system, lightning can cause fires, explosions, and equipment damage. The effectiveness of a ground rod depends on several factors, including firstly, the soil resistivity, secondly, the depth of the rod, and thirdly, the number of rods installed. Soil resistivity is a measure of how well the soil conducts electricity. Soils with high resistivity, such as sandy or rocky soils, are not as effective at conducting electricity as soils with low resistivity, such as clay soils. The depth of the ground rod also affects its effectiveness. Deeper rods are generally more effective than shallow rods, as they have a larger surface area in contact with the soil. The number of ground rods installed also affects the overall effectiveness of the grounding system. Multiple ground rods, spaced a certain distance apart, can provide a lower impedance path to ground than a single ground rod. The NEC specifies the requirements for ground rods, including the minimum size, material, and depth. It also specifies the requirements for bonding ground rods together and connecting them to the electrical system. It is important to follow the NEC requirements when installing ground rods to ensure that the grounding system is effective and safe. The grounding electrode system is a critical component of any electrical system, providing a path for fault currents and lightning energy to dissipate into the earth. A properly installed and maintained grounding electrode system protects people and property from electrical hazards. There are several types of grounding electrodes, including firstly, ground rods, secondly, ground plates, and thirdly, underground metallic water pipes. Ground rods are the most common type of grounding electrode. They are typically made of copper with galvanized steel and are driven into the ground to a depth of at least 8 feet. Ground plates are flat metal plates that are buried in the ground. They are typically used in areas where it is difficult to drive ground rods, such as rocky or sandy soils. Underground metallic water pipes can also be used as grounding electrodes, provided that they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. The grounding electrode system must be properly bonded to the electrical system. This is typically done by connecting a grounding electrode conductor from the grounding electrode to the grounding bus in the electrical panel. The grounding electrode conductor must be sized according to the size of the circuit conductors. The grounding electrode system must be inspected and tested periodically to ensure that it is functioning properly. The resistance of the grounding electrode system should be measured using a ground resistance tester. If the resistance is too high, the grounding electrode system may need to be improved. There are several factors that can affect the resistance of the grounding electrode system, including firstly, soil resistivity, secondly, moisture content, and thirdly, temperature. Soil resistivity is the most important factor affecting the resistance of the grounding electrode system. Soils with high resistivity, such as sandy or rocky soils, will have a higher resistance than soils with low resistivity, such as clay soils. Moisture content also affects the resistance of the grounding electrode system. Soils with high moisture content will have a lower resistance than soils with low moisture content. Temperature also affects the resistance of the grounding electrode system. Cold soils will have a higher resistance than warm soils. The NEC provides guidelines for improving the grounding electrode system. These guidelines include firstly, using multiple ground rods, secondly, using deeper ground rods, and thirdly, treating the soil. Using multiple ground rods can reduce the resistance of the grounding electrode system. The ground rod should be spaced a certain distance apart, typically at least 6 feet. Using deeper ground rods can also reduce the resistance of the grounding electrode system. The deeper the ground rod, the more contact it has with the soil. Treating the soil can also reduce the resistance of the grounding electrode system. This can be done by adding chemicals to the soil, such as copper sulfate. The chemicals help to improve the conductivity of the soil. The grounding electrode system is a critical component of any electrical system. It protects people and property from electrical hazards. It is important to install and maintain the grounding electrode system properly to ensure that it is functioning effectively. Understanding the NEC requirements for grounding and bonding is essential for ensuring electrical safety. Firstly, proper grounding and bonding practices minimize the risk of electrical shock by providing a low impedance path for fault currents to return to the source, tripping the overcurrent protection device. Secondly, a well-designed grounding system helps to protect electrical equipment from damage caused by voltage surges, such as those from lightning strikes. Thirdly, compliance with the NEC grounding and bonding requirements ensures that electrical systems are installed and maintained in a safe and reliable manner, reducing the risk of electrical fires and other hazards. In addition to the specific requirements for ground rods and other grounding electrodes, the NEC also includes requirements for the grounding electrode conductor. The grounding electrode conductor is the conductor that connects the grounding electrode to the grounding bus in the electrical panel. The NEC specifies the size and type of grounding electrode conductor that must be used, depending on the size of the circuit conductors. The grounding electrode conductor must be made of copper or other approved materials, and it must be protected from physical damage. The NEC also includes requirements for bonding the grounding electrode conductor to the metal water pipe, metal gas pipe, and other metal parts of the building. Bonding these metal parts together ensures that they are at the same electrical potential, reducing the risk of electric shock. It is important to consult the NEC for the specific requirements for grounding electrode conductors and bonding in a particular application. The NEC is a complex document, and it is important to understand the requirements before installing any electrical equipment or systems. Furthermore, local codes and regulations may have additional requirements that must be followed. Grounding and bonding are essential components of any electrical system. They protect people and property from electrical hazards such as electric shock, fire, and equipment damage. By following the requirements of the NEC and other applicable codes and regulations, you can ensure that your electrical system is safe and reliable.